Hey everyone, Aaron here. We're about to do another live stream today. The subject in this case is going to be just some tips and tricks related to using simulation inside of Fusion 360. We're going to get started in about 2.5 minutes, as you can see there, although we don't really start when that timer really lets up because we have a couple announcements to make and other things that we'll want to cover. Thanks for those of you who've joined us already. We're going to go ahead and do the little preamble right now, where we're gonna select like the winners from last week's draw. We're not going to do a draw next week. We're actually going to have a new presenter. I'm really excited about it. It's going to be Jamie Shearer. If you've been on Lars's channel, he actually did like an interview session with Jamie, which was really cool. But Jamie's going to be presenting T-splines, which I know a lot of you are interested in learning more and more about. He's specifically going to be using it on some generative results, but it's, if you want to learn about how to use T-splines, he is a great resource to hit up and listen to. So let's go ahead and do the draw real quick. As if you recall, it's for things like water bottles and stickers and chargers and things like that. So let's go ahead and just show my screen at this point so you can see the draw that we're going to be doing. So how it works is we just take the URL from the last live show, 360 Live. We throw it into this YouTube random comment generator, as I've already done here already. You can see I'm going to filter for duplicates, so don't try to just put 50 very short comments. It's going to get rid of any duplicates. So it'll find 27 unique commenters, and then when we hit start here, it's going to give us a winner to choose from, and it looks like it's Dobie 2003 EG. So he's telling us we have a perfect software. And I think I replied to him actually, and it's not perfect. There's a lot more that we want to do. There's a lot more that we can fix, and we're constantly listening to you guys, and we do appreciate his sentiment though. Definitely not going to be upset about that. So if you missed a little bit already, I just wanted to reiterate, this is going to be on again next week. It's going to be Jamie Shearer doing T-splines on generative results. I think it's going to be around the same time, but we'll just double check and verify before that happens. Make sure to check the channel. It'll give you an idea and reminder of when that's going to happen. I'll throw it in the community tab as well. So let's go ahead and just get started in today's content then. So I'm going to go ahead and just show my screen again. You guys might have saw this when I was switching between. This is this pedal assembly. We've used it for all kinds of stuff. It's neat because it presents a lot of different problems for us to address using Fusion 360, and very specifically in this case, we're going to be doing some simulations on it. So I'm going to try to show 3 different models today. I'm not sure if I'm going to have enough time to do just everything in this case, but I will try my best. It's not necessarily all about getting results. It's about showing you tricks and tips along the way, and hopefully helping you avoid the pitfalls and things that might stop you from getting your job done. So let's go ahead and just take a look at this real quick. And as you'll notice, and what we're going to be focusing on in this case is the accelerator. It does have like limiter bolts. I'm not an expert on cars and race cars specifically, so I'm not going to pretend to know what those are for. But what I want to simulate in this case is when it bottoms out, and the driver's still exerting force onto it. I mean, this guy's trying to go real fast, right? So when the driver's still exerting force and it's bottomed out, what happens? How is it going to react? Is it going to be strong enough to withstand the forces that we're assuming that the average human can exert on this? So that's the problem statement. That's kind of the layout. And then to go into running a simulation, all we're going to do is we're going to change the workspace into the simulation workspace instead of the modeling workspace. When you do that, if you have no study set up, it's going to present this to you. This is allowing you to choose from a number of different studies. And I put together this like single slide Google slide presentation that kind of runs down why you might want to use the different types of studies. I'm going to share that in the description at the end if you're interested in what some of these other studies are going to do. It's a good little reference sheet to have. It's kind of an interactive, I call it a one slide, but there's slides that tell you about each one of these different simulation types available here. So in this case, with the pedal, fully extended due to the bolt limiting its movement, we're going to do a static stress study. So we're assuming, there's going to be small deformations. We're assuming we're using like ductile materials that have a linear have a linear curve to their stress strain. At least for the beginning, right? And then also there's other assumptions that go along with the static stress study. Things like inertial effects are ignored, and other complex details that go along with like an event simulation. Let's go ahead and just select to create the study. That's going to pop us into our simulation setup essentially, and then we're going to start to create the setup that goes behind this. Now there's a little bit of pause there, and that's just because it's actually kind of loading all this stuff over into the simulation workspace. If I were to run a simulation on this entire assembly, that would be something that we would need a lot more than an hour's time to work on, right? Simulations can take a lot of time to solve. So it's something to be aware of, and you know what else I want to be aware of is that I say too much, so I'm going to try to avoid that. I've noticed that when I watch some of these live streams after the fact. That said, as I was saying, I want to avoid running the simulation on this entire assembly. I want to kind of simplify it, so that's what we're going to use this simplify workspace as this jumping off point within this simulation. What this simulation workspace will enable us to do is it'll enable us to just filter onto the parts of interest. And as I mentioned, I'm really just kind of focusing on the accelerator, but I want to include other components as well. So what I'm going to do here is I'm going to try to think about the different components that I want to include for the simulation to try to make it as accurate as possible, but while also making it solve very fast. So I'm going to select the face here. I'm going to select this bracket that actually kind of houses the bearings that it's rotating about. I'm not worried about actually getting the bearings and the bolts and all those details. Maybe I will get the bolt in this case, and I'm just selecting faces in this case, so it's not something that we need to like double click to get components, or I need to worry about selecting bodies or anything like that. Selecting just the faces is going to work for me, and I think that just about does it. Those are really the three parts that I want to focus on for this simulation. Once I've done that, I can right click and I can use this remove all except selected. This is going to get rid of all those other components. It's going to really allow us to focus in on just the pedal, the bracket that's holding it, as well as the bolt that's causing it to bottom out, right? So let's zoom out a little bit and we can visualize this. We are missing some components in here, but like it's components that maybe we don't build. It's maybe components that we're not worried about failing, right? Like the bearings and the bolts, maybe that to tie this down, we're not concerned so much about. So that has done a lot to enable me to get results very quickly. So with that, I think that's the only thing I want to do in Simplify in this case. I'm going to be showing Simplify in another example a little bit later where we can use some of the more advanced functionality there. But in this case, let's just keep it simple. Let's click Finish Simplify, and we're ready to move on to the next steps, which are to do things like define materials and constraints, loads, etc. So what's nice is that if you've defined materials in the design side of things, when you go to look at this, it will actually bring those over for you. This doesn't mean that the materials that maybe you selected or didn't select within the design side of Fusion 360 are going to be forced onto your simulation. As you can see here, you can change the study material to try different things, so maybe try lighter materials, to try less expensive materials, whatever your goal might be. With that said, I do want to keep these mild steel and aluminum 6061. The bottom bracket there is the 6061 aluminum. The pedal itself could probably be aluminum as well. Maybe that's something I'll try a little bit later. It's just another opportunity for us to compare results and learn more about this. But like I said, if you define the materials, we can skip that step. But it's always a good idea to verify what's in there. A lot of times, if your solution won't run, it's because of things like materials that don't have proper parameters defined. With that said, we'll move on to the next point, which is defining constraints. And I don't usually come up to this toolbar to grab constraints. I always just hit C on my keyboard. It's just really easy for me to remember. It's really easy for me to get to. C on your keyboard is going to enable you to get to these structural constraints, and we'll go ahead and start to define these. So if we think about this, there we go, I said again. We're gonna fix the bolt location here and here, because this is where this bracket is actually rigidly connected to the base plate of that pedal assembly. So we're gonna fix those two faces. Click OK. But that's obviously not the only fixture and constraint that we want to use. There's definitely more in here that we want to consider. I'm going to hit C again, and instead of using a fix this time, I'm going to use a frictionless. Now, what I'm going to use this next frictionless constraint to do is to represent the plate that's under this. Now, the plate that's under this isn't, bonded with some super strong glue. It's actually, free to slide. So this frictionless constraint is going to enable me to represent, that there's some rigid body on the bottom face of this bracket that's actually holding this pedal and the bearings in place. So we'll select that. I'm actually going to just stay within this dialog, because the bolt itself, I want to actually consider frictionless as well. It's not bonded to anything. It's something that is just, it's hit a face. We want it to stop there essentially, so we're going to apply a frictionless restraint there as well. Now, that's good and all, but the real important one is actually related to the missing components in here, those bearings that I keep referring to. We'll hit C again to bring up my constraints, and this time I'm going to use a pin. Now, what you want to do here is you typically, if you're using a pin, just keep the defaults. In this case, I want to stop the radial movements. I want to stop the axial movements, but the tangential movements I'm cool with. So that's why this one is not actually selected in this case. To define this pin, and actually it's going to do multiple pins, as you'll see here. I'll select a couple faces here. If I'm really concerned about getting every little bit of detail covered here and every little bit of information contained within this simulation, I might want to pay real close attention to where I'm selecting these pin faces. But in this case, I'll just select these three faces. Once I click OK, I can jump over to the browser where all these things are getting added to the simulation setup, dig into constraints, and you can see adding that one single pin actually broke it down into three separate pin locations. That's going to be related to each one of the faces that I selected. So we're not necessarily pinning these faces together like you might do with like a bolt or something. In this case, we're just pinning those cylindrical faces, getting rid of the movements as described in the previous setup. Okay, so we'll continue on, and I think the last thing, and this is really probably the easiest thing for people to visualize and to understand and to apply. This is where you actually apply the loading situation. So in this case, we could hit L on your keyboard, or of course you can use the drop down at the top. I like to try to use keyboard shortcuts whenever possible. It just helps me to stay focused on the task at hand. I should also mention that these waterfall sort of menu structures, your mouse gesture structures, will enable you to get to things like structural loads and constraints and contacts, which we'll talk about in a little bit later example. So just like that, we've got into this force. Now we're going to select the target. So if you think about where the foot is applying the pressure, it's going to be on this face. What I absolutely love about this is that we can very easily, play with the angle that it's being applied, or use a reference face to try to direct it in some way. But in this case, the way that I'm imagining the biomechanics of the foot is pushing on this, I'm going to assume that it's actually being applied normal too. So I don't need to get into any of those details. It's something that we'll just skip past in this case. But there are quite a lot of flexible options built into these direction types that if you're looking to apply in different directions, and you definitely want to dig into these. So just like that, we'll set this as 75 pounds. Could be higher, could be lower. In this case, this is just what I'm shooting for. We'll click OK. And just like that, I think we are pretty much almost set up There's other things we can do, and there's other checks that we can go through, but let's go ahead and actually do one of those right now. Let me just come up to this guy right here, and this pre-check icon I've kind of been keeping an eye on. It starts with a big red X, and it's telling you, hey, you're not ready to run this yet. It looks like it's not quite ready, or maybe it is. This yellow exclamation point is saying, there are some potential issues. It could just be, related to the type of study that you're doing, or, there might be some interferences that you need to deal with. And this is a really handy tool to help you root out and deal with those issues. So let's go ahead and just look at some of these. So let's just take note of those. The interferences one, it could potentially be an issue. I kind of might have overlooked that in the simplify. Luckily, it's very easy to re-access. But the other thing it was talking about there was the degree of freedom plot. This is super handy. If you click on this, it's going to highlight, whether parts are fully constrained or whether or not there's some freedom of movement. In this case, the pedal itself and the bolt that's attached to it are partially fixed, and that's because the only real fixtures on it don't get rid of all degrees of freedom. So in the bolt's case, it has that frictionless constraint on the bottom face, so it can slide along that face any which way it wants to. And the pedal itself has that pin constraint in the bottom area there, and that's allowing it to continue to rotate. So there's potential for this to be an issue, but we know that some amount of rotation or some amount of freedom to move is sometimes okay for these simulation setups. So we'll take that in mind. We'll pay attention to what the coloration means here. What's nice is that if you have a really big model, you can actually come in here and set ones that are not a problem to invisible. It really helps you to filter down, and I didn't learn about this until quite a while after I had been using this degree of freedom plot. But pay attention to these options. You can set these to invisible, so you can dig into a very complex model to figure out where those issues might be. And the other nice thing is that you can keep that up. So if there's faces that you want to go and apply things like contacts to, which I will be discussing in the next example in more detail. This is something you can keep up, so you can visualize your changes as you make them. So I'm going to actually close out of that right now, and let's jump back into Simplify Workspace to make sure we have no interferences. Interferences in simulation are typically a bad thing that you don't want to have happen. And the way that I think is easiest to explain is, if you have two faces or two bodies and are interfering with each other, maybe the software will be able to mesh those faces, but what does it do? If there's conflicting forces acting on it, or it's just mathematically it's introducing a lot of problems, and that's what a lot of what's going on with these simulations is a lot of mathematics. So with that said, let's fix this, and there's a super handy tool here to do this, and this is something that I absolutely love about this, and I use it all of the time. This interference tool. So what you'll do is you'll just select it, and you'll use it just like you use an interference tool within Fusion 360 normally. I'm going to just highlight every single body in this, all three bodies, big whoop. But I've selected all three bodies there. I want to select the compute button now. And what it's done is it's found, that bolt is maybe the model itself encompasses where the threads might be, so it's actually a little bit bigger than it actually is going to be in real life. So there is some interference there. So what we want to pay attention to is what is going to get cut and what's going to get kept. So we can play with the tool, and we can play with the target, so we can just verify which one we want to cut. In this case, I'm not too worried about it. We'll just go ahead and click OK. I don't really care if the sliver of the pedal gets cut away. I don't really care if a sliver of the bolt gets cut away. We're talking about a very small area of interference in that case. Okay, so that's good. Let's finish the simplify. And at this point, we're almost ready to go, but there's that other thing. The contact between the bolt and the pedal itself has not been dealt with, and contact's really important whenever you're dealing with multiple parts or multiple components inside of a simulation. Easiest way to deal with this is obviously automatic contact. So I'm going to just select my automatic contact. This tool's fantastic. If you have small gaps, typically you leave a little bit of gap for tolerance and things like that. This will enable this tool to overcome those gaps to still apply the contact. Now, the only area that should really have contact is between the bolt face and the pedal. In the other cases, I don't really want contact between, say, the side faces of this and the side faces of the bracket that's actually holding it. So I've created the contacts, but where are they actually located? Let's go ahead and select this drop down once again to be able to manage those and see where those are. It looks like we got 3 contacts, and it's the cylindrical face to the cut in the pedal. It is the bottom face to, and it looks like I did actually cut the bolt face a little bit, so there's a little bit of overlap. There's a tiny little face there that can be bonded as well in this case. Again, not something I'm overly concerned about in this case. But just like that, I think we're good to go. Let's go ahead and select the solve button. We can solve this on the cloud. For a very simple problem like this, I'm much more apt to use the local solver. It's going to be faster anyway. So let's just select local, verify what we're solving there, and click the solve button. Now, a problem like this, real simple. It should come back in minute or two. This is a very simple simulation, and I think it has a pretty coarse mesh as well. So we'll go ahead and start solving this, and we'll hopefully get some results real quick here. And I'm going to show my face again. We actually got a new light I'm pretty thrilled about. So you can see me better. I don't know if you guys actually want to see me, but we're trying to do a lot more of these live sessions, so we're trying to invest a little bit of money into the production value, right? So let's go back into Fusion. It looks like the simulation has finished, so we're starting to see some results. What I want you to always pay attention to when you get these results are things like how it's deflecting and where the stresses might be, because that'll tell you a lot about what's going on here. So for a 75-pound load acting on this, I definitely wouldn't consider it to ever be close to failing. And in fact, this factor of safety is much lower than I'd expect it to actually be. So let's try to figure out why that might be. Let's do something here. Let's actually, and before I get too deep into the weeds there, I do want to show you this nice tool will actually tell you whether or not you're on target for what your goals might be. I mean, different industries, different types of design have different goals and safety factor targets. So here you can play with that. We're just using the default. 3 is usually pretty good. For a performance automobile, like 2 or less is might be acceptable. Anyway, let's go ahead and close that, and let's try to figure out where this issue might be, and we'll just zoom in, and you can see, okay, there's this real small kind of sliver face here that has a very high stress, but an extremely low safety factor on the flip side. So we're not really concerned with the bolt, and we're not really concerned about those results either. The reason for that is that there's a potential for what's called a singularity. When I post the recording for this, I'll actually link to a quick tip we did on singularities. It's common in every single finite element analysis. It's just related to the mathematics behind it and the faces that can get created in CAD. So it's something to pay attention to know about and to pay attention to and to ignore when you can. So in this case, I'm not actually, concerned about the bolt failing at all, and it's not really what I'm designing today. So I could do something like I could come in here and I could actually, I could find the hardware and I could just hide it. And when I hide it, it actually recalibrates the safety factor. Now it's telling me my minimum's actually like closer to 4, and it's actually on this face down here. So we're starting to get more information about this, and we're starting to feel a little bit more secure about the performance of this pedal. That said, there's obviously more and more results available to us. If we change to a stress plot, we're looking at some nice stress results there, and this is not as coarse as I thought it was. If I click the little lamp here to hide or show things, you can see the mesh quality that I'm looking at here. I had intended to use a coarser mesh, and I can show you how to adjust that in a second here, but There we have some results. We can start to parse the data and not to overlook the importance of post-processing and looking at these results. Let's continue on to look at some different ways of analyzing this. The other thing I want to do is I want to animate this. This is a really good pre-check to do. This is kind of like a sanity check. It's a good way to verify that you've set the problem up properly. If it's deflecting in the way you'd expect, then that's a good little pre-check to do. I usually like to turn on like a two-way fast, and if you really want it to look cool, you can increase the number of steps here. And then if we hit play again, we can get a nice little animation of this deformation. Please do note that that doesn't deform that much under that 75-pound load. If we look at the displacement plot, the actual maximum displacement is 0.01 inches. The reason why it looks so pronounced is this deformation scale. It has an automatic adjustment that it does. We can go further than that if we'd like to, and if we go and animate this again, it's going to look real wonky. But it's a good way to check. It's a good way to verify that you've set it up properly. So that's nice. We've simulated this first case, but say I wanted to try maybe a different material, or maybe I wanted to try to make the pedal a little bit easier to manufacture or something. Let's go ahead and try another example real quick here. I'm going to click simplify. And what I want to do is I want to clone the simulation model. Now the simulation model is basically what I've taken from the overall model. I've removed all the other components and I've really focused, and I've also done the combined cut, essentially, is what happens when you do that interference check. So this thing's basically ready to go. Maybe I just want to make a quick change, maybe cut some more material out because the factor of safety is high, or something to that effect. This is a great way to dig in and try different things. So I always like to clone it. It's going to take all my simulations setups that I've done, and in this case there's only the one, so we'll just click OK to that. And now we're in the new simulation model, Sim Model 5. Looks like I practiced on this a couple times, and we're actually simplifying this some more, and I can do some things here, like maybe I could remove features. In this case, I'm going to just do a real quick removal of features just to enable me to get through more of these results and get to those other models that I was talking about. So using this tool, we can get rid of all the fillets and chamfers and like pockets and things like that. Be careful if you're too aggressive with this. This process can actually take a while to compute, but in that case, it's a pretty simple operation. But using that defeaturing tool, we can very quickly get rid of like small details that can actually cause the simulation to run very slowly. That's part of what the Simplify Workspace is intended to do. It's also to do like I showed you at the beginning, to like focus on small areas of a larger assembly. But just like that, I mean, I've got rid of all these chamfers and fillets and some of the holes and some of the pockets. I can go and solve this again. I'll get some results much faster than the last example. The reason for that is all those fillets require small elements to capture all the details there. This thing will come back in no time at all. The results will obviously be slightly different, but I just wanted to get another set of results essentially, so I can show you a great tool to use if you're running a lot of simulations. So in this case, it ran again. Looks like the minimum factor of safety with the bolt hidden again. It actually saved all the visualizations that we're using in the results as well. So you can see it's got rid of the bolt again. So the minimum factor of safety for the pedal itself is 5.6 in this case. What's really cool when you get into a lot of these different results is that you can control select these, right click and select compare, and this compare workspace enables you to use the same camera view. You can sync the camera view, you can sync the scaling for the safety factor or results. Check the synchronization options. I'm going to synchronize result type and max min. That'll enable me to very quickly figure out where the highest stresses might be between the two cases. And you can see this guy definitely gets to a higher stress. There's like very little red area on the part to the right. So is that a better design? No. I mean, it's going to be heavier, and there's other things going on there. Like I say, I really wanted to do that so I could get results really quickly to show you this compare workspace. So you can do up to 4 different comparisons at once. I find this to be incredibly helpful because you get tons of results back and you want to kind of figure out what's the best plan of action from what you've been running and what you've been figuring out from the simulations you've been running. Okay, so that's the first intro model that I wanted to show you. The next one I'm going to be getting into is this crane hook. It introduces some nice options for me to show you some additional lessons here. So let's go ahead and open up this crane hook, and this is something I pulled off GrabCAD. It's just an example file that I thought would present some nice options for us to learn from. So I'm going to create a new simulation. Sorry, this one's already been created. So if you already have a sim model set up, I'm going to hit simplify. You can right click and create a new simulation from scratch. So that was the finished version. I'm going to be showing you perhaps at the end if we have a little bit of time. But in this case, this crane hook has to basically handle a 5,000 pound load. It's a real simple setup. I'm going to click simplify, finish simplify to get out of this dialog, and then do another static stress study. Now, the lesson for this case is going to come into, how do you apply the force properly? Because the way that this hook has been created, there's not really a great area or face that I could apply this to. So that's something that I want to show you, and something that we can use some of those load direction tools to really play with and get accurate results from. So let's do a real quick setup here. Let's just hit C on our keyboard to constrain the face on the pulley maybe. We'll hit L on our keyboard to start to set up the loading situation. And as I mentioned, it's the problem that arises is that I want to apply the force to where I imagine like a chain or something is actually, or cable is resting in this hook, and that's where the force is actually going to be applied. It's not going to be applied to this entire face or this entire face. There's actually some nice ways of dealing with this and getting rid of what's in there currently. One really quick way to try to deal with this is but there's a limitation to it. There's a really quick way of trying to deal with this, and that's using a limit target. So if I select the face that I did previously, select the target to be this guy, you get this option if you have a single face selected. So this limit target enables you to kind of force whatever value you're going to type in here onto this small circular face. Now you can move it around. You can see I can just click and drag on the tip there to kind of move it to different places. I can rotate it. That's not really going to do any good. I can drag the size up if the chain that's going to be attaching this is in contact with a lot of different faces. But the problem is that this actually falls upon these two faces. If I go to select another face to apply this to, that limit target's not quite going to work for me. So there is something else that we'll need to do, and that's going to require that we go into that simplify workspace for a real quick second to fix this up. So I'm going to jump over to simplify. I'm going to create a sketch, and I'll just use this face to sketch upon. It doesn't really matter in this case. I just need a planar face kind of looking at this from the front. And I'll just draw like a circle in this case. So I'll just grab a center diameter circle. This is a good representation of the area that might be in contact with the chain, as I mentioned. I'll draw the circle out, and that's it. That's really the only bit of sketching I'll need to do. In this case, I'll just go and I'll finish my sketch. So I'll click Stop Sketch. I'll hit S on my keyboard, and I want to do a split face. So I start to type in SPL. It's going to help me filter to the split face command. And now I can select the faces to split, which will be these two faces, the splitting tool, which will be the circle that we created. And it does a good job of helping me visualize how it's actually going to split this. And what I realized previously is that there's a couple additional faces in here in the back here that we might want to split as well. So we'll select a couple more faces there and click OK. And now we have this really nice area that we could apply this force to very accurately represent where these loads are going to be applied. So we'll click Finish Simplify. We will jump in here and hit L on our keyboard to apply the forces. We're going to select, we're going to select all the faces for our targets, and make sure, I do that all the time. I don't know what it is. I might have hit a keyboard shortcut or something that did it, but make sure that you're applying targets still instead of using the reference as I had switched to there. So just make sure that it's being highlighted properly and applied properly. One thing that I want to point out is if you're applying something to multiple faces, this removes any ambiguity as to what the value is that you're typing in here. And the value that I want to type in eventually is going to be 5,000 pounds. So I'll just type it in. And I don't want 5,000 pounds on each individual face. This pulley is not designed to handle that much. So we'll just do 5,000 pounds split amongst those faces. This is going to enable me to ensure this, avoiding toggling. This is going to enable me to avoid overloading this in a way that I don't want to. Okay, so that's looking all right. However, the direction is way off, right? So let's see if we can use, we could use a vector in this case because it's actually just going, downward, but that's not as fun as doing some of these other options. So I'll use the angle option, and to be able to define the angle that we're going to be using, maybe I'll just find like a flat face on the top that's going in the direction I want it to go. So I'll select that as the reference. And just like that, now my force is being applied directly downward with the direction of the load that's on this crane hook. So perfect. That's exactly what I was looking for. There's so much flexibility in the loading directions and targets and things like that. So make sure to pay attention to this. Just like that, we'll click OK. And I think that's really most of it. If I check my degree of freedom plot, we're going to see lots of red here. The reason for that is that no contact has been dealt with. So let's keep that open in this case. We're going to keep the degree of freedom plot open. I'm going to select my automatic contacts. We'll keep the default tolerance set. We'll hit generate. And in just a second, we're going to see a lot of these red ones turn to green because it's found contact between those. However, there are a couple pieces in here that do not have the contact defined. These pins, for whatever reason, are not, there's that tolerance that's built into them, right? They need to fit through those holes, and so that's why we are not seeing the contact, or it did not recognize the contact when we used the automatic option there. So let's use the drop down here to use maybe a manual contact to address this. So we can select one of the pins and one of the faces, and then what's really cool about this is that it filters through all the other parts. This is so incredibly helpful because the thing about these faces, these contact faces, is that they're usually really hard to get to because they're hidden behind other parts. So make sure to select selection set 1, and this is actually dialog box is a little bit smaller than I need it to be, but I'll use the toggle to change to selection set 2. So I selected one of the faces on the pin. Now I'm selecting one of the faces on the side there. Just like that, we've actually addressed the contact there. Now it's actually found the contact. And contact is not something to overlook. I'm using bonded contacts quite a lot here, but there's other contact types that you'll want to pay attention to, things like separation, sliding, rough, and bonded. Rough will just basically add friction. Sliding will do just like it sounds. Separation allows for separation. The reason why I'm using bonded in these live sessions mostly is A, it's the default. B, it's also going to solve the fastest. When you do things like separation and sliding, it's a much more complex analysis, and it's a lot more mathematics that's going on there. Anyway, I do not want to do that 7 more times. I mean, although this is green, it's not connected on the back face there. So the reason why it's green is that there's a connection somehow going through this to connect that, but really it doesn't know that this face is touching this face. So it's a little bit misleading. I mean, if you solved it and you looked at the results, you could tell right away. But let's go ahead and address this with some more automatic contacts. But in this case, we'll just compensate with the tolerance that is between the pins and the pieces that I would like them to connect to. Be careful if you make that tolerance too large. You're going to get a lot of contacts that you don't want to have happen, so it's something to definitely pay attention to. But just like that, we've created this. Now let's go ahead and solve this real quick once again locally. And actually, I did say I wanted to get these results very quickly, and I'm actually a little bit behind schedule is where I wanted to be. So let's do something here. Let's jump into my settings. This is one way to get there, but in your settings, you'll find an option for adjusting your mesh. This is, all the way to the right, which is going to keep it pretty coarse, to be honest. But there's additional ways to get it coarse, and there's a lot of reasons why you do want a coarse mesh, for the first run. It's because there's typically a little bit of troubleshooting that you'll do as you're working through this. So I like to first pass analyses, keep it as simple as humanly possible. Use the dumbest, coarsest mesh. Your results will be garbage, and we're not going to take those as final results at all. But it is something that we want to get back fast so that we can continue to iterate on the simulation setup, because there's a lot of that happens. So back into our sim setups, what I was getting to is to make it run even faster, we can get into the element order, which is going to change us from a second order element to the first order element. This linear element is going to reduce the number of nodes and therefore get us our results faster. Another thing that I'll use in this dialog, I'm not going to use in this case, however, is the scale mesh per part. So if you have some really small parts and some really large parts, this will do a good job of compensating for those smaller parts and to scale the mesh appropriately for that case. Like I say, though, I do want to try to keep this as coarse as possible to get those results as fast as possible. So we'll just hit solve and do it locally once again. Keep this number 2. This is our second study that we're doing here. Take a quick drink of water and we'll watch this as it solves. Hopefully we get some results back in no time. Oh, let's see, what can I talk about? AU is coming up, Autodesk University, and we're in some very heavy preparations right now. So I am doing 3 different little classes there, one on simulation, just like we're doing today. So hopefully I can reuse some of this content actually. So while that solves, so I'm solving locally, and the reason for that is it should solve relatively fast, and we want to get those results back as fast as possible during these live sessions. But a good reason to not use the local solve is that I can't do anything when it's solving. I had to just show my face, and I had to talk about random stuff. So if you send it to the cloud, you can go and set up your next study. You can do all kinds of stuff. It's an incredibly helpful tool and way to get great results without tying down your computer too much. So looks like we do have some results now. Our factor of safety is within what we're shooting for. If we look at a stress plot, we start to gain some additional insight into this. The main goal for this lesson was really about how to apply how to use the split faces to apply those loads on areas, more accurate areas, but also the automatic contacts, manual contacts, things like that. So hopefully that was a valuable use of your time. The last example that we're going to do here is really just wanted to show you this Beagle board that I was working on. Someone on our Eagle team created this very complex board and asked me to run a thermal simulation on it. So I wanted to show you some of the more advanced simplify commands that are available to you to be able to actually run something like this when it opens. Hopefully it opens in a second here. When it opens, you'll see just how incredibly complex these designs can get. I mean, it's really up to the componentry that you have in your libraries that build these up from Eagle or your ECAD system. Probably should have opened that before. And in just a moment, we will be looking at the Beagle board. And the other thing that I probably didn't test is I didn't actually, run all these, simulation studies, keep them open in the background, and continue adding to the processes that are going on my computer. Looks like it did just open, so we'll switch you back to my screen, and you'll probably really quickly understand why something like this took so long to open. There is a ton of detail in this board, and you're only seeing a portion of it because There's like hundreds and hundreds of holes in the board itself. There's pins all over the place. There's just all kinds of stuff going on here. So this is where Simplify makes your life much, much easier. So let's see how to use it. Let's just jump right into the Simplify dialog. And the first thing that I might want to do is I might want to just get rid of the case. In this case, this is just in the way, basically. Now, when I selected that and right-clicked, I didn't get the remove that I was looking for. The remove all except selected was there, but I don't really want to do that. So if I double-click, it'll get the component. I hope everybody knows that shortcut. So if you right-click now, I can select remove. That's going to get rid of the bottom portion of the case. The top case here is transparent. Let's do one more quick remove. And there you go. You're starting to see the details that go into this. I mean, there's decals and stuff that actually show you all the traces and stuff. Beagle bone. Sorry, I don't know what this thing is. It's one of these like programmable boards. That's beyond my capabilities in terms of electrical design. But what I wanted to show you is just how quickly and easily we can simplify something like this. So let's get into it. So first of all, this remove feature, you saw me use it on the pedal. Wasn't probably the best example. In this case, this board itself has like thousands of holes that I want to get rid of. So if I select it, you can start to see this Christmas light effect, and each one of those lights is basically an area where it's going to fill in a hole. And that's okay. I mean, for the simulation's sake, those holes are not going to add detail that I need to be able to figure out what maybe the maximum temperature of the chip is going to be, right? So using this tool, we can very quickly and easily get rid of all of these little details that we don't want. We can grab this slider and move it to the right. We can filter for particular types of things. So if you're getting fillets and you don't want to get fillets, you can clear this option. But in this case, it's doing really well. I'm going to just hit the X there. It's going to clear out all these holes for me. And very quickly, we're going to be able to mesh this thing in probably like a quarter of the time. I mean, each one of those holes will have to have elements all around it. So getting rid of these small features is something that is not to be overlooked for a simulation setup. And like I say, the more highlights, the more Christmas tree lights that you see in this image, the longer these processes are going to take. It looks like it finished, and it still stays open, which is nice because I still want to use this maybe for some of these other components in here. It actually is taking the liberty of highlighting some of the other features now, but I'm going to clear the current selection and maybe move to a different piece. Like maybe I want to simplify. We'll just use one of these old doohickeys here, plugs. I'll select that, hit delete. It doesn't work all the time. There's actually cases, I think, on this particular part itself where it was having issues. So if that happens, if you're having issues with using this, or if it hits some sort of limitation, use things like the remove faces. This remove face will do something really nice for me. If I want to just fill that in, like these guys don't produce a lot of heat. I do know what little I do know. That's one of the things that I'm pretty confident about. These guys don't produce heat, so I can just fill them in and they'll mesh faster. So using this, a combination of remove faces and simplify, we're able to get rid of a lot of the details there. But by far, for getting rid of tons and tons of details, this replace with primitives is incredibly helpful. And this used to be limited to, I think, Fusion Ultimate, but with the merging of the two, this is great to be able to show everybody this and that everybody has access to all these tools. This chip itself, I know, has tons and tons of details on the bottom of it. One thing you want to pay attention to when you're doing this replace with primitives is whether or not you're selecting bodies or components or whatever it might be. In this case, it's set to bodies, and that's not what I really want. I want to replace the entire component because this chip is multiple layers, and there's reasons for that related to the actual design of this. But this box replacement will get rid of all these little pins that are on the bottom of that otherwise would cause the simulation to take forever to run. Just like that, we've replaced that. We can do this some more here, like get rid of this little capacitor. It has some details that we don't want. Box obviously is not the right selection here. We're going to select cylinder instead. The shape direction is something you want to pay attention to, so I'll use the y-axis here. Sorry, z-axis. And it's a little bit too large right now, and what I'll do in this case is I'll just zoom in and kind of try to get close to what I'm after. The reason why it was so large is it's actually there's the flat square on the bottom of this is still part of the same component, but really what we want to represent is the main cylinder piece, so I'll just shrink that down and we'll replace that just like that. And so on and so forth. There's a lot of different details here that we might want to get rid of. You could hide the decals. That'll help you to visualize this a little bit better. But with the combination of simplify, replace primitives, and replace features, you're going to be able to very quickly get rid of all the details of that board and simulate this for the thermal simulation that I actually had done on this. So I think that does it for today. This is a little bit on the longer side for these live streams, so I hope it was valuable. There's a lot to show. Make sure to subscribe. Make sure to like this. Jamie's going to be back next week. He's going to be showing you all about T-splines. I think it's going to be at 10 o'clock next Tuesday, 10 o'clock Pacific, but pay attention to the time. He hadn't really tied that down yet. I'm really excited to see what he's going to be doing, and thanks everyone for watching. Keep fusioning.